Naimbagal daw, architects and civil engineers of the future. Welcome to the Eiffel Tower. I mean, welcome to your online class in strength of materials or mechanics of deformable bodies. I am your instructor, Daryl J. Amblebeen. In this video, I will discuss bending stress example 3. The cantilever beam in figure A is composed of two segments with rectangular cross sections. The width of each section is 2 inches, but the depths are different, as shown in the figure. Determine the maximum bending stress in the beam. The beam is under a concentrated load of 2,000 pounds at point A. In this problem, we can actually sketch the shear and moment diagrams immediately without even solving for the support reactions. But let me first solve for the support reactions at the fixed support at point D. So at point D, we will have a vertical reaction dy, and it acts upwards because it will counteract or balance the downward external force, 2,000 pounds. And its magnitude is just equal to 2,000 pounds by summation Fy equal to 0. So dy is 2,000 pounds. For a fixed support, there ought to be a horizontal reaction dx. But since we do not have any external horizontal forces, dx is just equal to 0. And for a fixed support, there is a moment reaction. We call that md. Its sense is clockwise because it will balance the moment created by 2,000 pounds, which tends to rotate counterclockwise about point D. Now let's solve for md by taking summation moment at point D equal to 0. So we have positive md because that is clockwise, and 2,000 tends to rotate counterclockwise about point D, hence negative. And its perpendicular distance from point D is 8 feet. Equating everything to 0, we get md equal to 16,000 pound-feet. Now we sketch the shear diagram. At point A, we have a downward external force of 2,000 pounds. So we go down to negative 2,000. Going from point A towards point D, there is no external loading. So all throughout from point A to point D, we have a uniform negative 2,000. And at point D, we have a vertical upward support reaction of 2,000 pounds. So we add negative 2,000 at this point plus positive 2,000, which is equal to 0. So we go back to 0. In our shear diagram, we went from 0 back to 0. Next, we sketch the moment diagram. At point A, there is no couple, so we begin with a 0. And we add the area of this whole rectangle, which is base times height. Our base is 8 feet. Our height is negative 2,000. So 0 plus 8 times negative 2,000, that is negative 16,000. So how do we connect 0 and negative 16,000? We simply connect them with a straight line. So our moment diagram is a linear graph. Since in the shear diagram, that is just a horizontal line. So a horizontal line in a shear diagram becomes a linear graph in a moment diagram. So at point D, we have a clockwise moment of 16,000 pound-feet. So we add negative 16,000 plus positive 16,000, which is equal to 0. So we then go back to 0. In our moment diagram, again, we went from 0 back to 0. Okay. The cross-section is not constant. At segment AB, the depth of the cross-section is 4 inches, whereas at segment BD, the depth of the cross-section is 6 inches. So the maximum bending stress may either occur at point B or at point D. We know now that the moment at point D is negative 16,000 pound-feet. But how about the bending moment at point B? We can calculate that using our shear and moment diagram. So to get the moment at point B, we simply get the area of this rectangle, the base of which is 4 feet and the height is negative 2,000. So we add 0 plus base is 4 feet times height is negative 2,000. So that is negative 8,000. Therefore, the moment at point B is negative 8,000 pound-feet. The moment at point B, just to the left of point B, is 8,000 pound-feet. And the moment at point D is 16,000 pound-feet. Next, we compute for the section modulus of segment AB. For a rectangle, it is given by the formula BH squared over 6, where B is the base, H is the height. Substituting our values, our base is 2, and our height for segment AB is 4 inches. Therefore, the section modulus of segment AB is 5.33 square inches. Next, we compute for the section modulus of segment BD, still given by the formula BH squared over 6, wherein our base is still 2 inches, our height is then 6 inches. Therefore, the section modulus of segment BD is equal to 12 square inches. We're now ready to solve for the maximum bending stresses at point B and point D, given by the formula absolute value of M over S, where M is the bending moment and S is the section modulus. So let's first consider the bending stress, maximum bending stress at point B. At point B, the moment is negative 8,000 pound-feet, but we get its absolute value, so we have 8,000 times 12 to convert that into pound-inch. And the section modulus is 5.33 square inches. Therefore, the maximum bending stress at point B is equal to 18,011.26 psi. For the maximum bending stress at point D, the moment at point D is negative 16,000 pound-feet. We get its absolute value and we convert that into pound-inch. So we multiply 12. And the section modulus of segment BD is 12 square inches. So therefore, the maximum bending stress at point D is equal to 16,000 psi. What now is the maximum bending stress in the beam? That is equal to 18,011.26 psi, which occurs on the cross section just to the left of point B.